to introduce David. My great pleasure to introduce John to you this morning. This is the start of a series of geology presentations that John has organized for us, and he'll tell you more about that. We're starting this morning with him and David. John completed his undergraduate studies in geology and then an MNC also in geology at the University of Natal in 1976. And then he did a PhD in geochemistry at UCT in 1981 on the geology and origin of the Karoo volcanoes preserved in the Lubombo monocline, which stretches down the eastern margin of South Africa. Thereafter, he spent 2 years on a postgraduate study of volcanic deposits and processes in the Western USA. And he was based at the University of New Mexico in Albuquerque. Now, John subsequently pursued a successful career in the local and international diamond exploration and mining sector. Initially with De Beers, and then in his own business and with junior mining ventures. He and Marilyn now live in Hermanus, where he and colleagues of the Overberg Geoscientist group, some of whom you see here, they all colleagues of the Overberg, having what he calls an exciting and highlighted time, highlighting the remarkable geology and the related, I seem to have lost my, and the related features of the Overberg region and the Western Cape. So specifically the Overberg region and the Western Cape is what we find this group really preoccupied with, and it's wonderful that they come and share their insights and their experience with us. Looking forward very much to the talk this morning. Thank you, John, over to you.
Okay, well, thanks, Letitia, and thanks, Gert, and thanks to the U3A members, and thanks to the Overberg Geoscientist group as well for all participating in this. And yes, just to very quickly state that this is the first of 4 talks, all on a Friday for those that don't read their emails. So until the end of May, we'll be talking on a Friday. And then we hope to follow the talks, weather permitting, with short field trips to the relevant sections that we talk about. So today, Dave Mourant is going to talk about particularly or mostly Clarence Drive and the basement geology, the geology that underlies and supports all the rocks that we see on the surface. So just to introduce Dave, and then Dave and I are going to do just I'm going to do a few minutes of just background with a few slides and then give it all to Dave. So Dave was brought up in the UK and completed his BSc honours at Sheffield University in 1971, specialising in mining and economic geology. Like all good geologists, he ended up spending 3 years in diamond exploration in Zimbabwe. Thereafter, he joined Goldfields as a mine geologist and ended up, interestingly, in a technical department, setting up their computer system, and then stayed there. And then subsequently, Dave and his wife Anne bought a small farm in Barberton in 2002 and spent a long time regenerating the natural environment of that area. Dave is a great environmentalist. He's also a very key member of the hacking group in Betty's Bay, and they are doing a great job cleaning up the exotics and invasives. Dave also did a course in environmental management at UNISA. And most importantly, he was part of the team that set up the Barberton-Mkonjwa Geo Trail, and he'll just tell us spend a few minutes on that this morning. As I think most of us know, that's now part of the Barberton Mountain Land World Heritage Site. And so he has great experience on setting up essentially or highlighting the geology or geology for lay persons, and we look forward to sharing that idea. Anyway, thanks, Dave. Thanks for making yourself available. Thanks for your hard work to date on the Clarence Geo Trail, Clarence Drive Geo Trail, and over to you, and then back to me, I guess.
Thanks a lot, John. We're going to be looking today at, first of all, the basement, and then where it actually outcrops along the Clarence Drive. And I see from some of the people there, there's probably a great deal more expertise out there than there is necessarily behind the screen on my end. So a lot of people out there have contributed to what we know. Okay, John, back to you.
Okay, you're going to have to run me through, Dave, so you keep next slide.
Yep.
Okay, so just talking about the geology of the Western Cape, we all get very excited about the Table Mountain group because it's always there in your face. And then we sort of progress onto the Bokkerveld, which overlies the Table Mountain sandstones, and that's where all our, or most of our agriculture takes place. But if you look at this diagram of majestic Cape Town, you'll see there's the mountain, and then on the left-hand side is rocks referred to as the Malmesbury group, and then the Cape Granites. Obviously, those of you who go to Stellenbosch, well, or not Stellenbosch, but particularly Paarl, will know of the Paarl granite. So Dave's talk today will focus on the Malmesbury and the Cape Granites, and because it's Clarence Drive, he'll also talk a little bit about some of the TMG, the Table Mountain sandstone, excuse me, quartzites. So that's where we starting in this journey of ours will be to look at the basement rocks. How did they get there? At what age did they get there? And what were the processes that put them there? So that's as I say, where we're starting, and from there we will work up the geological column, and that's what the effectively the 4 field trips will, or the 4 presentations starting today will do by the end of May, and then the field trips will hopefully take us out and actually show us some of the rocks. At this point, I just want to say that this is work in progress. None of us in the group, and you saw probably a list of names on the first slide, profess to be experts on all of the topics we are covering. And so we really value, as Dave just said, the info and the efforts of all the experts out there and your support. And we'll certainly be interacting a lot more with those people. Carry on, Dave. Okay, so this is just a summary, and one of the things we still have to do is with people like John Rogers and John Compton, and that is really work out the age progressions and the times when most of these key events happen. So we've got the geological column wrong today. We put it upside down. But we're effectively going to be talking to the Saldanian orogeny. So that's when these Malmesbury rocks and Cape granites were formed, and we'll show you how we think they formed. And then, as I said, Dave will move on briefly to some of the Cape Fold Belt stuff, because there's some gorgeous exposures of rocks of the TMG around on the Clarence Drive and Betty's Bay as well. Next one, Dave. Okay, just in terms of our objectives, the first objective is really just to highlight the remarkable Overberg geology. If you look at that just picture on the side, we have climate change on our doorstep. So we look there at Hermanus, which is sitting on a 30-meter platform or old beach, probably formed about just less than 4 million years ago. And it's on our doorstep, and we need to, take note of these examples. And if people get worried about climate change, well, the fact is it's going to happen. We live on an old platform, which is very, very much part of older climate change. Next one. And the second part of our objective is really to share and communicate the geological endowment and benefits. Next one, Dave. keep it simple, and really take it to laypersons, scholars, and kids. As I said, we're not professing to be young, new, upstart geoscientists trying to turn over all the work that good and experienced people have done. We actually want to take geology to laypersons, and hopefully in the course of the 4 talks and then the field trips and subsequent plans that we have, we'll demonstrate that. The other thing that I think people tend to forget is that rock minerals, soil, water, and oxygen shape our environment and daily life. The room that you're sitting in right now is all made out of stuff that comes out of the ground. Again, the agriculture is all on soils, altered rocks, and those soils provide the food that feed us. And obviously the other important part of all of this is water. Without water, there's no life. So last one there, Dave. And then of course, we all forget to, some of us I think probably don't forget that all the technology, the stuff we're using today to actually have this presentation, again, comes out of the ground, and that's computers. That computer box on the right-hand side, quite remarkable when you think that the cell phone to the left of it probably does about, 10 of those old box computers can do. Next one, Dave. So the geotrails that we are currently working on, and you'll hear from the people that are the experts are working on them, is Clarence Drive. That's the topic today. Next one, Dave. Then the Overberg, that gorgeous area that many of us know up the Palmead River. So that's on our target as well. The Hermanus Cliff Path, John Blaine will talk about that next week, and the geology. The one, and it's great to see Chris is on the, Chris Hartnady's on the talk, the hydrology of the Table Mountain Group. Chris and Rowena, hey, their company, Voto, has done some superb, or has done all the work with our municipality here in Cape Town, unlocking the hydrology of the Peninsula Group, which is at the base of the Table Mountain Group. And we look forward to having Chris or Rowena or one of their team also talk to us about the remarkable work that has been done, and what it all means to A, the Western Cape, and then B, potentially South Africa. The Hemelin Wine Valley, for obvious reasons, and that'll be a good fun project. It again takes us onto the Bokkerveld rocks, which support most of our agriculture in the region, particularly the wine farms. And I think Cameron Penn Clark is also on the presentation today, and he's going to talk about the Bokkerveld rocks in a week or two. And then we have this remarkable geology, the cave dwellers, the human origins, all of that stuff around the corner at the Kelders, and we really need to make more of that. So we'll be doing that, and that's Mike Dormer's domain. We're also going to get Hayley Cawthra to talk to us about the young geology. I think some of you have listened to her in the past. Thanks. Next one, Dave. And then Mike is also with his colleagues, and I think Harry Van Aswiegen's also on the talk today, pulling apart the geology of Gansbaai area. And very interestingly, they already have Dave's rope trick being set up in the village, and also building a rock garden, which at some point we'll talk more about as well. Thanks, Dave. Next one. And then the last one is just the acknowledgements. As I say, a lot of people have already been very helpful and forthcoming, and we look forward to further interaction with those people. And that list is by no means complete, so we will continue to add to it as we go along. Carry on, Dave. Okay, and that's just a little map that shows where we've been focusing our efforts. I think you're all familiar with the coast. If you haven't been around Clarence Drive recently, you best go and take a drive. That's typically Dave's trip to the supermarket. Dave lives in Betty's Bay, and I think they go shopping in Somerset West just to experience the scenery. So Clarence Drive, there's the Overberg that you all know, and then obviously there's the focus around Hermanus, and then down to the Kelders and Gansbaai. Next one. Okay, over to you, Dave. Thanks.
Thanks very much, John. I'd just briefly like to start off with some background on what we did in the Barberton Mountain land to set up the Barberton Machondra geotrail. We can learn from this and also perhaps in some cases learn what not to do as well. Information panels were set up. There was 12 of them on the road between Barberton and the Eswatini border. But each of the panels was absolutely specific to that site from a geological point of view. There was other information in terms of historical, geomorphological, etc. Information. They were on separate panels, and I'll be showing you some examples of both these types of panels. But it was the geology was very specific. Had to be accurate, and we had a couple of people who were initially doing the text, and then it went through committees and it got sent to various academics, professors, etc., who then made sure that it was accurate because their names were going to be associated with it, and hopefully we'll be able to do the same thing here. But it had to be understandable to the general public, not just to interested geologists or people interested in geology as such, but just people who were driving along the road and saw these things, and we needed to make it understandable. There was a very major effort on the graphics. The whole of the, as you'll see in a moment, the whole of the panels, the information panels, were effectively pictures. There was not just text, but it was all relevant to the particular site. Very important that nothing much was said away from that in the actual specifics. Say the graphics were integrally part of the information, and a lot of people find it very much easier to retain or gain information from a picture rather than the text. And it was that made people stop and look at them. So it was, it's very important. And as I say, I'll show you the slide in a moment. You can actually see, I hope. Yes, this is where it is probably the most difficult part of the entire process, was cutting down, not only on the amount given on each panel, but the sort of level of it. We really had to be very, very careful about how much we said and at what technical level we said. So let's just have a look at one of the panels now. This one is concerned with the formation of the red beds, the banded iron formations, and we separated each panel into 3 areas. This part of the panel was a maximum of 200 words, as basic as we could to get across the information. We aimed it at sort of school children, 8 or 9, 15, 16-year-olds, that sort of level. And indeed, we took schools up there and made sure that we could get this information across. So that's where people started it. Then the center panel, this was, if we could manage it, a graphical or picture representation of what we had been talking about. So this gave you what was happening in a picture form. And as I said, a lot of people found this much more easily retainable, and if not comprehensible. And then the third part was specific to that site. These are pictures of the site. This is the overall picture and some details of the banded iron formation. So this was to bring the other 2 parts into focus at that particular point. We could also get a little bit more technical here, because we hoped that we had already got across the what we're looking at and the formation. What we're looking at here, how it formed here, and this is now the final result, what they were looking at, what they could walk over to. And we tried to make the panels literally that people could read it, look up and see what they've been reading about. So that's the principles on which we worked to get our 12 technical panels. Then there were, apart from that, we had 3 or 4 of these scenic panels, 180-degree photography and graphics. And here we introduced a lot of history, a lot of environmental information on the vegetation and the animals and birds around that area, and the history of what had gone on, the mining, particularly up in the Barberton area, but even going further back than that, back into the Boer War and so on and so forth. So these are a very attractive way of getting people involved in what they're looking at. And as we've written down there, the ideal place that we can think of for one of these panels would be up on the end of Rotary Way, where you've got a panoramic view. And to set this up and give information on each particular aspect or each particular area on there, I think would be a very, very good idea. There may be more that I don't know about. There are a couple of others that we've got in mind, but that one I think is a must do. Okay, that's the actual panels mounted there. Each site had we had to build a lay-by, and the majority of the cost of the geotrail was involved in making these lay-bys. We don't necessarily have to do that along Clarence Drive. There are numerous of these lay-bys along there. The information panel, as you can see there, it's you can get an idea there of the size and also the type of building almost that we did. It's a very solid mass. It's the rock, the quartzite underneath was very well built, and the concrete which actually contained it was again very well done. We had to make sufficient room around them so that a number of people can gather around, and also make them strong enough for my grandson to be climbing all over it. In order to counteract the potential vandalism, we made sure that the actual information panels were inset into the concrete, because otherwise before we did this, we found that people were starting to pick at the corners and see if they could lever them up. The panels were very expensive. We had to get them made in the States, but I gather subsequently that the processes and the materials involved are now available in South Africa, so it won't be as much of a cost, but one must be careful of the potential for vandalism. There was very little on the panels. That one of the semicircular plinths with the 180 degrees, we were driving through there one evening, and people had set up a little braai fire in the middle of it, which wasn't quite what we had in mind, and we did ask them to stop. As I say, the material was chosen to be resistant not only to human damage, but to UV. They were totally UV protected, if you like. So very important. You can see there the attraction of the graphics, the place that they're shown, the thing on which they're mounted, and that is the way to go. We may not need them quite so big. I don't know. That's what we're working on at the moment. But those were, we found, very, very effective. Right. Okay. With that over, let's go back to what we are meant to be talking about. We're going to be looking at the formation of the basement rocks on which the Table Mountain group have been deposited. I want to, first of all, cover the generalities in terms of some of the processes going on in the Earth at the moment. And I imagine most of the geologists concerned will certainly understand and hope perhaps be able to contribute. Then we're going to look at the specifics, and then we will drive, in inverted commas, along the Clarence Drive and have a look at some of the exposures along there. Okay, so we're going to start off with how it was formed. This is a generalized section through the Cape. It shows the basement Malmesbury group. It shows the granites, the Cape granites that were intruded into that. And on top of it, the Table Mountain group rocks, which have been subsequently folded, and then eventually the Karoo sequence on top of it. Now, this is, as I say, a very generalized thing. We're going to now look at how this basement formed, and then what happened to it prior to the deposition of the Table Mountain group. I can press the right button, just to give some idea of the ages that we're looking at. This is the formation of the Earth about 4.6 billion years ago. During the Precambrian, we start off life, the oldest evidence of life is somewhere around here. And John would like to say that there's a prize for anybody who spots the spelling error in this. The oldest, the Barberton Mountain rocks that we were talking about were also deposited in about this area, about 3.5 to 3.2 billion years ago. There the evidence of early life, but during the next 2-3 billion years, we started to come down to get more evolved life, and we started around 600-700 million years ago to get to multicellular life. The ages that we'll be talking about roughly are in this area, either side of the Cambrian formations here. Okay, if we're looking at a bit more detail here, right down in the immediate Precambrian and the Cambrian up to Ordovician areas in the Table Mountains. But for the Malmesbury series, we're looking down at that immediate Cambrian, Precambrian boundary. Right, in order to be able to explain how and where, in fact, the Malmesbury series were deposited, we have to have a brief look at plate tectonics, or seafloor spreading, however you would like to. I don't quite know what it's called now, but that's roughly what we're looking at. Okay, so here, Africa, South America at the moment, the Mid-Oceanic, Mid-Atlantic ridge here is the site of the development or the creation of new seafloor due to the hot magma rising, erupting onto the seafloor, forming new seafloor, and at the same way spreading the Atlantic, moving Africa and South America further apart. It's very, very slow. It's been happening for a long time. In fact, in 1382, Christopher Columbus sailed across the Atlantic. If he had to go there now, he'd have 25 meters further to travel. So the Atlantic has increased by about approximately 25 meters in that time period. So the things are very, very slow. Still reckon he would have found it, but anyway. The other aspect that we'll be looking at is what is happening here off the South American Pacific coast, where the Pacific floor is being subducted underneath South America. And as it goes down, it heats up, forms magma, and forms the Andes, the volcanoes in the Andes, and also creates a lot of the earthquakes, things that happen in that area. So let's have a look in a little bit more detail how this process is involved in the formation of the Malmesbury series. We'll have a look at that subduction zone, as I say, similar to the Andes, where the oceanic crust is subducting underneath the continental crust as it heats up. So it forms volcanic activity and intrudes granites. And there is a wedge of sediment along the front, like would be the Andes, but we'll see where it is in our. And this is where the Malmesbury series rocks were initially deposited. Let's take it a little bit more detail. Here we have on the left the area of what is now the African continent and the South American continent. Now, the time that we're looking at was when the Gondwana was being created. And here, South America is busy moving towards Africa and effectively docking into the west coast there, and at that time creating the eastern part of, sorry, western part of Gondwana. The Proto-Atlantic here was where the Gondwana sediments were being deposited. So these were sandstones, muds, shales, and a few other things, but primarily those type of deposits, quiet water deposits, deposited in here. As South America came across and docked, so it was all squashed. This would be the Malmesbury series in here. The magmas came up and created the Cape Granites. South America and Africa docked to form a part of Gondwana. So here is what the area that we've been looking at here. So we've got Africa, South America, Antarctica, India. This is the Falkland, the eastern peninsula of the Antarctic, and the Falkland Plateau is in here. So this was at the end of the docking procedure. South America had docked, had squashed the Malmesbury series sediments, and we're now waiting for the next episode to happen. And we'll just cover this quickly. The Gondwana had been formed, but here we started a rift, if you like, similar to the Red Sea today, where there's tension, and the Falklands Plateau and the Antarctic Peninsula started moving away and opened up the Agulhas Sea here. So we have tension with Africa here, the Falklands Plateau moving that way, and that allowed the erosion of the existing sediments down into the Agulhas Sea, where the Malmesbury group were forming the basement on which these sediments were deposited. So the Malmesbury group had been formed by the compression involved in South America docking to the west coast. Then there was the tension down in the southern part where the Falklands Plateau moved away. The surrounding rocks were then being eroded down into the Agulhas Sea, which was underlain by Malmesbury group. The formation of that, when South America docked, it would probably have formed a lot of the mountains in the Malmesbury group, but these have been planed off and we're now forming the basement there. Then, reverse of the movement, the Falklands Plateau started to come back due to probably some subduction down here. And this started to fold the Cape sediments. Eventually, this is up to about 300 million years, the Falklands Plateau here formed the Cape Fold Mountains, and the erosion of this mass eventually came down into the Karoo and formed the Karoo here. We have a lot of this type of fold, and we've all seen it in the mountains, and we will be seeing it when we do the field trip here. And there's types of folding. Some of it is one is called harmonic folds, where all the layers are doing the same thing, but then there are discontinuous or disharmonic folds where it's probably due to slumping rather than merely compression. And there are examples of this disharmonic folding just to the east of Hermanus there on the mountains. I can't remember the name of what they're called, but just the other side of Fernclough. But they're very much the disharmonic folds. Okay, so we've had the formation of the basement. We've had the deposition of the Table Mountain group. John Blaine will be going through this, I'm sure, in a lot more detail next week. And then the folding and creation of the Karoo series, well beyond what I want to cover today. Okay, around 180 to 130 million years ago, Gondwana broke up and formed basically the geography that we know at present. India moving up this way rapidly to impact into Asia and form the Himalayas. And most of the mountain ranges that we know at the moment were formed by the impact of various parts of Gondwana into Laurasia. Don't want to go into that too much at the moment. It's a little bit beyond where I wanted to be. Let's now return to the Clarence Drive. This is a picture taken above Keuchel Bay, looking out towards Royals here on the right. And I think everybody has driven along there, but it is magnificent, really amazing piece of scenery, I think. Right, as one drives along there, there is a big lay-by on the coastal side, and it's labeled Blowstien. Now, the Blowstien referred to is, in fact, the Malmesbury series, the Malmesbury rocks of the Tygerberg Formation. These were, in this area, mainly sedimentary, but there are some volcanic ignimbrites, obviously formed by the volcanic activity that we noticed earlier on during the docking of South America. The Cape Granites formed at approximately that period. And these, as we've said, were the equivalent of the modern Andes, whereby we've got compression formed by subduction, we've got the volcanic and igneous activity to form the granites that we see today. Planed off to create the basement, as we saw in the diagrams a few minutes ago. And here on at the Blowstien, we can actually walk down to, have a look at, and put hands on, literally, that contact. These are some of the rocks of the Malmesbury series. So these aren't in this area. These are in fact up in on the west coast, but it shows very clearly that they are sedimentary rocks formed in underwater in the sea. You can see here the cross bedding very clearly, and some other shaly, sandy sedimentary features in the rocks, proving that they were sediments. Now, if we have a look from a drone, which we have a tame drone pilot, Gavin, who will be taking a lot more of this type of work for us. We have a look here at the Blowstien, the Malmesbury group in this area, the dark grey, blue-grey rocks here, overlain by the pale, in this area almost horizontal, slightly dipping away from us here, Table Mountain group sandstones. And this outcrop is it's not really visible from the road or from the beach, but we will be getting some more very good pictures of it. You can see here a car here, so you can get some idea of the scale. What we plan on doing with the field trip is walking down into this area, just along here from the road. So for those who intend coming along it, it is a bit of a scramble down and back up, but there are paths. Okay, this unconformity here, this line represents a gap of probably around 60 million years. Though the Malmesbury group, when we say the age there is 600, that is the start of the formation of it, not this particular bit. One can't date sediments very easily, so we're not 100% sure of exactly the age of these rocks here. On the other side of the road, the Clarence Drive, this is near Sparks Bay, looking at Cougar Bay, the actual resorts there. In this stream, these are the Malmesbury series rocks, and here the mountains are set quite a way back from the coast, as opposed to everywhere else along Clarence Drive when they're right next to you. And what happened here is there was a very gentle anticline, a dome folding, and the Table Mountain group then were weakened by this folding and got eroded back. So we're left with quite a large valley. You can see it, this is goes along here, back up, which is all underlain by Malmesbury series rocks. And at some stage, we're going to be having a look at the vegetation in this area to find out how it differs from vegetation in for instance, the Bockerveld, the Renosterveld, on the shales and on the sands. And I'm sure we can find almost a way of mapping by the botany, as it were. These are some of the outcrops on the side of the road just near there. And the honeycomb weathering is probably due to some calcium carbonate, limestone or something like that, which has been eroded by solution, by slightly acid rain. I haven't had a look at it in great detail, and would probably, I think we need some help here when we do have a look at it and drive through. I'd love to know what exactly caused that. Down on the beachfront, inverted commas, there are some big boulders and outcrops, and you can see here the deformation involved in the docking of South America. It took a line of what were probably pebbles in there we are, along here, and they've squashed and deformed them. They're almost teardrop shaped, some of them, and you can also see the deformation in the sediments here. Very interesting outcrop. But again, when we do the field trip, we'll be able to go and have a look at this in more detail. Okay, the other aspect of the basement are the granites. And unfortunately, we don't get any really good outcrops of the granite in this area. Where it does occur, which is Humanada and near Stanford, it's very oxidized and very poorly exposed. This is obviously a picture up in Paarl, which is the typical outcrop. Would be wonderful we had some of that around here, but we don't. And for the interest, granites do make a very, very stable and good kitchen counter. And these are the minerals typical of it, the quartz, feldspar, and the dark mica, biotite mica. There are some other interesting outcrops and occurrences along there, along the Clarence Drive. This is just part between the Blowstein and the going towards Royals, and it is in the Table Mountain sandstones, and it is manganese. And this outcrop was at some stage investigated to see if it would be mineable. And there is a tunnel there, one can climb into it. It goes back about 6 or 7 meters. And obviously they found there wasn't sufficient manganese to warrant it. The manganese is occurs along there. There is a fault and some major jointing, which has allowed mineralized waters to flow down through it and to concentrate the manganese in this area. These are some close-ups of this conchoidal, where there was a cavity here and the deposition of the manganese around it. And here the interesting part, it shows that the manganese was coming in long fractures. This lower part is a much harder rock, which under stress has fractured. And the fractures have subsequently been infilled with manganese, whereas this overlying layer is slightly finer grained and it didn't fracture. It may have bent and buckled. There are no fractures in it. Therefore, there was no manganese deposited along it. Above this, there is more manganese. So this bed here, it was not as brittle and didn't fracture like these beds below it and above it. So all these places we want to highlight in our geotrail, and there would be probably a major information panel in the Blowstein lay-by at the bottom of the hill there. Unfortunately, we're going to have a problem with access. The road in this area around the manganese is very narrow, and we may have to approach the roads department to try and build some sort of a path for us along there. But it really is well worthwhile. There are other aspects to be seen there, which we won't be covering today. This is taken from a honours thesis by Paula Hutchinson, working with Professor John Rogers, and I must admit, her work and her thesis has formed a large information source for us on this drive. She did, I think, a very, very good job there. This is actually her, the picture was taken by Prof. Rogers. Okay, so we're seeing here the Malmesbury outcrop of somewhat metamorphic, very low-grade metamorphic rock, and some of the talus here is actually formed from this. So we know that this was an exposure at the time. I'll come back to exactly the time later, but you can see the talus above Paula there is layered. There are very definite layers within the outcrop along here. And this is not the only place one can see them. This is just a particularly good photograph by John and Paula. So one can see that the possibility is that all these layers, different thickness and the different size of rocks in them, is due to changing weathering. That may be due to, in cold weathering, ice age type, a lot more fracturing, whereas warmer period, less fractures. So there was finer grain material being washed down. The age of these major deposits along the drive is not, I don't think is definitely known, but it certainly seems to be greater than 35 million years. But I'm well prepared to be have different information there. Okay, there is right near Royals, there is, again, this is derived from work done in Paula Hutchinson's thesis. These are the same talus deposits we were looking at, and there is a dune here, which is definitely a shallow marine dune, because there are shell and sponge debris in it. So this was deposited much later. And then on top of this is the modern talus deposited in the last maybe Holocene, 10,000 years. Very interesting. One can go and look at it and see this is about 30 meters above the present sea level, showing, as John said earlier on, that there's been quite a lot of change in that due to the climate changes. Let's keep moving. The clock over there seems to, right. As one drives along between Royals and Pringle Bay, on the left-hand side there, there's a very clear indication of the stratigraphy of the Table Mountain group. One can see the negative weathering shale, the Cedarburg Formation here, with no major outcrops in it. We've got and also there's a lot more vegetation. Shales have a great deal more nutrient than the sandstones, and so there's a very different vegetation in this area. The Peninsula Formation, very clearly high ground, as the Overberg as well, up here, forming the tops of the mountains. The Pakhuis is a Tillite, a glacial formation. I'm having a look at it in just a moment. So this is very clear. You can see very easily the stratigraphy in the area. This is the glacial deposit, the dimectite or Tillite, the Pakhuis, and this is also potentially a place that we were going to go on the field trip. This is on the extreme western end of the Silver Sands beach here at Betty's Bay. It's called Arsbunk, and they're very clearly, they're beautifully washed. The hard quartzite pebbles deposited by the glaciers as they melted, and subsequently these sandstone infilled dikes appear to be cracks that have been filled in with a very similar sediment to the Tillites. I'm going to keep moving quickly because I'm going to be running over time if I'm not careful. Okay, as one moves further towards Claymont, just outside of Betty's Bay, there is very clear evidence of recent activity in terms of rocks falling down from above. This is very clearly very recent in geological terms anyway, since the end of the Ice Age, probably Holocene, maybe 10,000 years. And certainly when we moved to this area a few years ago, it was very clear, I made it very clear anyway, that we were not going to buy a house on that side of the Clarence Drive, because there's a potential for rocks to come down there still. And when people ask me, how often do they come down? Well, if you count up the number of rocks that have come down and say they all came down in the last 10,000 years, you get a very clear average when it comes down. I realize this is not a very technical way of doing it, but we certainly weren't going to buy a house in that area. Okay, I think that's really, just want to come to our conclusions. And this is the kind of thing we want to be able to put in brochures and eventually panels along here. And I say we're very, as John said earlier on, we're really at the beginning of it now, gleaning information, and we're certainly going to be hoping that a lot of other people can share and probably control what we're putting in. So Malmesbury sediments deposited in the what's called the Adamastor Ocean to the west of the southern African continent at roughly those times. Docking of South America during the Sardinian orogeny. As we've seen, there's a lot of folding and a lot of deformation of the Malmesbury series rocks. Cape Granite's intruded around about 540 million years. Rifting and spreading of the Agulhas Sea, followed by the deposition of the Table Mountain group into the shallow marine basin, the Table Mountain group. Okay, that's about it from my point of view. And please have any questions, and I hope John will be able to answer them. Thank you.
Thanks, David. It's Gert going to unmute us and open up the video. We can chat. Thanks, Gert.
Why don't you stop your share and show us your face, Dave? Thank you. John, too.
Okay.
Put on your video.
Apparently you have to turn it on. Yep.
Unmute us. Here we go. Okay.
Thank you.
Question times, and who won the prize?
Well, I wasn't in the competition because Hans and Gert's fingers are quicker than mine. John and David, that was absolutely fascinating. You know, it's wonderful that we're able to share this platform with the geoscientists, and you have so much to teach us and share with us. I find it fascinating, and it was so clearly put out and explained, and it makes me want to go on one of your field trips, even in weather like this. Thank you very, very much. It's a wonderful privilege that we're able to share this platform.
Great.
Look forward to the rest of the course.
Thank you, Dave. I also found it equally interesting. Can I ask you, where did the what was the intrusion? It wasn't magnesium. What was the intrusion that you showed? Where did the manganese intrusion come from? Where did the manganese come from?
It would have been distributed in the overlying rocks and concentrated by water percolating through, dissolving it. I don't quite know the conditions under which it would have to be, with temperature and pressure, normally mineral springs, that kind of thing, then percolating down. John?
Well, we've got some experts on the talk, and maybe we should ask them. But interestingly, Gert, manganese is the 13th most abundant element in the earth, and it actually moves quite quickly in solution. You know, once you get the EH and the pH right. And you know, we find, for example, that the manganese deposits that produced some of the world's best manganese up in the Kuruman, you know, Northern Cape, was actually a secondary deposit formed in the banded ironstone formations. So manganese is very mobile, and if you get the right conditions and you have big fractures and faults, you know, it really moves very, very readily. But there's a lot of it around the Cape. I mean, there are other areas, and maybe Gordon Chunnett or John Compton or John Rogers can comment. You know, there's several other manganese mines, so to call. None of them really became big mines or economic, but there's a lot of it around.
Yeah, I can interject on that if you like. I had an MSc student, Duncan Miller, who studied the supergene manganese deposits in the Cape Peninsula, and included some analyses on that deposit that you mentioned. Basically, it's leaching of the manganese and the iron, of course, from the Table Mountain group, and then this would be under reducing or acidic conditions, in which case both manganese and iron become mobile in the solution. And then when those solutions reach the atmosphere with high oxygen content, they precipitate out as iron and manganese oxides. So when you look up at the cliff faces, you often see the bright orange to yellow colors. That's the iron oxides that have precipitated out. And you'll also see the black, which is the manganese. And so they're very redox sensitive. They're very sensitive to the oxygen reducing conditions. And normally they're just superficial deposits. If you were to take your rock hammer and chip away at them, you would see the relatively fresh sandstone underneath. They form a very thin deposit. But within the fault zones, where, as David mentioned, the fluids are concentrated, this is where you get these more substantial manganese and iron deposits. And they're very well displayed within the fault zones in Skeleton Gorge, for example, and in other faults within the Table Mountain Peninsula. So that is quite an interesting master's done on that. And if you want the nitty-gritty detail, you can go to UCT and look up his thesis. You can download it as a PDF. So it's there for anybody who wants to really get into the nitty-gritty. He did a lot of interesting chemical analyses on both the manganese and the iron content. So you might find that of interest.
Yeah, and he's actually on the presentation, Duncan. You're very quiet there. Duncan, you're going to talk to us.
It's Duncan McGregor. Duncan McGregor.
Oh,
not
sorry.
Duncan.
Sorry. It was Duncan McGregor. Sorry,
Okay.
my mistake.
Not Duncan Miller. Okay, all right.
Sorry.
Thanks.
I guess my age is catching up with me here.
Are there any other interesting mineral intrusions other than the manganese and iron you mentioned? Is there gold or any of the other things that intrude somewhere?
There's tin in the granites. Maybe John or someone, John Rogers. Are you a tin expert? Tin in the granites.
I'll ask Chris because he went to the tin mines near Table Mountain.
Okay. You got to unmute yourself, Chris.
There's
Chris?
also tungsten in
Yeah.
many of the granites in the Western Cape.
Okay.
Sorry, I was muted there. Yeah, I've lost touch with tin in the Western Cape. I wouldn't like to comment in any expert way at the moment.
Okay, you become a water expert.
Yeah, I've left tin behind, I'm afraid.
Okay. Anyone else?
But they are probably late hydrothermal deposits after the intrusion of the Cape Granites. That's about all I guess I would say.
Yeah.
Sorry, another layman's question. The Malmesbury group, it's all sedimentary rock. There's no igneous rock in that area. Is that true?
There's no igneous rock in this area, though I think there is some ignimbrites up in the Darling, up in that area. Though I speak under correction, John.
Yeah, the main, can I comment on that? The Overberg strand has kind of basaltic andesites, and has dated them, and I think they're around about 550 million years old. So, and that dates the Tygerberg formation, because Hartwig-Frimmel has also got concordant uranium lead ages out of zircon from the Tygerberg formation, and the youngest age, as my memory serves me, is about 556, I think it is. So the evidence is that there were zircons were being produced during volcanism at about 550 million years when the Tygerberg formation was being deposited. That puts a kind of maximum age on the deposition of the Tygerberg group, I guess. Apart from the andesites or basaltic andesites at Overberg, you do get the again, mafic rocks in the Swartland up along the Berg River, the so-called Bridgetown group, or Bridgetown rocks, and they are basalts, and they're overlain by dolomitic carbonates. So, and we assume that those are parts of the former Adamastor Ocean. So they are these, call them ophiolitic fragments, also in the Malmesbury group as a whole.
John, I see there's a question in the chat room. Could you just answer that?
Okay. Right. Could these mass movement deposits possibly be linked to seismicity along this region? Could these mass movements, I presume that's the reference to the big rocks that fell down. Chris?
Hi, John. Yeah, sorry, it was me asking the question. Tawfiq Dancer here. Yeah, so the recent ones, and even these old ones, you know, this well, I should say relatively older ones, like you were showing this one picture that the honors student had done. So would this possibly maybe be you know, some kind of a paleoseismicity that we see along this area?
Okay, well, I mean, Chris again is the seismic expert for the Western Cape. But Chris, do you want to comment a little bit on seismicity in the area, past and present?
What one has had big collapses. For example, of Table Mountain, there was one sort of south of Fernwood Buttress. I forget how long ago, but that was not associated with any earthquake. We have these very steep cliffs with highly fractured quartzites, and occasionally some just break loose. maybe there could have been some, so it's not entirely seismically related, although the abundance of big rock falls around the place does suggest that if something like the, and we had the example in 69 in series where there were rock falls and rolling rocks from the Witzenberg associated with the seismicity then. So the assumption is that very many of them might relate to former earthquake events like the 69 event in the Tilbach series area or the 1809 event in the Milnerton area. Yeah.
Okay. Does that answer, Tarif?
Yes, that does. Yeah, also, I mean, since you're getting these big structures coming through that area as well, it does kind of make sense as well. No, thanks a lot, guys.
Yeah. Look, I mean, the area has obviously been through many structural events, and I think Gerry van Aswegen, who's a rock mechanic expert, he's been playing with Mike Dormer and measuring fractures and joints out around Gansbaai, and it's quite fascinating to see, the jointing that's pervasive throughout our area.
Yeah, in fact, maybe if I can just jump on, there's a big sort of a neotectonic feature as well around Gansbaai, isn't it? That Marco Andrioli and co has seen, where the I'm not sure what the unit is called, but it's where the aeolianites are essentially juxtaposed against this one structure. So that's also quite an interesting structure that I think it goes right through this area as well, if I'm not mistaken. It's kind of a northwest, southeast oriented fault as they had mapped it as. I know Ake and one of his students recently did some work on that area as well. So yeah, very interesting region.
Okay, well, Gerry and Chris again.
Yeah, I can't remember the name of the feature. It'll come back to me, but there is indeed in that Frans Kraal area and off to the east of that, along that contact between largely Bokkerveld and TMG type stuff and the aeolianites, there is this this linear feature which is assumed to be evidence for former a surface breaking fault.
Yeah, it's called the Blomerus fault. I just remembered now.
That's right. Yeah.
John, what does one call a collection of geoscientists? A conglomeration of geoscientists. It's wonderful to be able to be eavesdropping on your conversations with one another. I think that's very special. Thank you for creating this platform for us, and we look forward to all the presentations still to follow in this course. Thank you very much. My conglomeration of geoscientists.
Yeah, thanks, Letitia. That's quite appropriate. Yeah.
Sorry, one other quick question from my side. Is the elevation of the Bokkerveld, of the Malmesbury group reasonably constant, or does it vary a lot along our coastline?
I don't know about the coastline in general. I can only really say about here, and it is pretty constant in this area. I'm afraid I don't know sufficient about it on the West Coast. Perhaps Messrs.
John and John.
Compton, it is.
Very seldom seems to form the mountains on the West Coast, all just above sea level. And
Yeah, quite right. It doesn't really form, major landforms. I mean, you get little bits of it sort of standing up here and there, and then it erodes quite quickly as well.
Yeah, the general idea was that you had an erosional peneplain that formed with uplift and erosion of the basement rocks. So both the granite and the Malmesbury shale were presumably weathered down to quite a large peneplain structure. And then on top of that was deposited the Table Mountain group. So I don't think it tends to show a lot of elevation variation within the Malmesbury.
Can I just mention that John Compton summarizes a lot of these things he's been saying in his new book called West Coast: A Natural History.
Yeah.
Yeah,
it's a great book.
Indeed.
And I think I'll be speaking to that book specifically at some later date, when John Bristow and I organized that. So more to come on that later. Hey, John.
Absolutely, John. Yeah, no, we look forward to that, and that's what we need. I mean, we're going to do the grassroots base level stuff, and then we'll bring in the experts to tell us how it really happened.
Excellent.
Ed?
Yes, go ahead, Jenny.
Sorry, I've got a couple of questions. The first is, which mineral makes the Malmesbury shale such a dark grey colour?
Okay. Essentially, it's so the Malmesbury is, and the experts again can correct me, but we're having fun getting to unravel the Malmesbury, and I've just recently sent a bunch of samples to Ted Thatcher for thin sectioning and XRD, so we'll be able to give you the full story in a couple of weeks. But the Malmesbury are basically shales and siltstones, and shales sort of almost by definition are sort of consist of very finely ground up material. And they carry a fair amount of dark minerals. I mean, they have iron and manganese and those sort of things. There's not much quartz left in them. So shale, shale, if you then metamorphose it or compress it, then becomes sort of we see shales, for example, in the Table Mountain group, and they get quite dense and dark rather than white as per the sandstones. I don't know if that helps.
And also I might add, it's the organic matter content.
Yeah.
So
thanks.
Normally when we speak of shales, we often speak of black shales, and black shales is reflecting the fact that they have very finely broken down bits of organic material. So even though animals hadn't really evolved by the time of the Malmesbury shale, certainly algae had. And so presumably that dark color is imparted largely by dead organic remains of algae that were living in the sea at the time.
Thank you. That's very interesting.
In my book, I put in a thin section from the Robben Island Tigerberg Formation, and it seems to be mainly quartz and biotite mica and pyrite.
Okay, you had some more questions?
My second question was, to what extent was the underlying structure of the Malmesbury shale affected by those sections of the shales which came in contact with the hot igneous intrusions of the Cape Granite suite?
Spotted hornfels near the sea point contact.
So it did change the underlying, the structure, the contact areas. It sort of cooked it.
It changed them to a contact metamorphic or thermal metamorphic rock called hornfels, which is crushed up in quarries in the Tigerberg for road aggregate all over Cape Town.
Oh, that's very interesting. Thank you.
I'll ask a question, John.
Hi, John. Good to see you.
We get South America pushed up against Africa and well cemented in the orogeny which developed there. Then it all pulls apart again. There has to be some very fundamental reason to move things one way and then suddenly turn around and move them the other way. Is there anyone able to comment?
Okay, who's the expert? Chris, yeah.
Yeah, I think I don't know if anyone has seen this this movie, A Billion Years in about a few minutes, and it's what is called a full global plate tectonic model of the last billion years. In other words, the transition from what used to be the Rodinia supercontinent to Gondwana to Pangaea, and then the breakup since then. So, and that's if you home in, you can almost go in and grab frames every million years throughout this, and basically it's the way the subduction zones are moving they're consuming ridges, they then rolling back. And in fact, what is called the Adamastor Ocean turns out in that new movie, which only produced in the last 6 or so months, late 2021, it's a University of Adelaide. It's part is an addendum to a recent scientific paper in Earth Science Reviews. So it's worthwhile looking at that. But basically, what it's telling you, in an answer to John Truswell's question, it's telling you that the subduction zones around this part of Gondwana, when it was forming, were actually quite complex. There was something called the Adamastor Ocean, which then extends up towards the Mozambique Ocean along the East African side of Gondwana. But then there was something they now call the Clamene Ocean, which actually separated Amazonia and some of the South American fragments from the Rio de la Plata craton. So it's these different subduction zones and how they're interacting with each other that give rise to phases of compression and then the opening of back arc basins again, that kind of thing. And there's been an attempt to work this out now in full quantitative detail, which is quite interesting. There's some parts I don't quite agree with, but it's something that, using new plate tectonic software, there's something called G-plates that people can play around with to do this kind of modeling. And that's what's going on at the moment. So I throw that in.
Fantastic, Chris. So can we get that link from you? Is it available? You send it to me and we'll circulate it to the U3A and our group.
I'll look it up again and circulate it. Yeah, I don't have it in my head or on my machine at the moment.
Fantastic.
But, yeah.
But it also goes back to the point that those old sutures sort of remain, points of weakness almost forever. So if you go and look at our cratonic structures in the Karpvaal, the ancient cratons are still they're almost coherent since the Archean.
Yeah.
Okay.
One more question about the Malmesbury group. How far up the east coast does the Malmesbury group stretch?
John? Chris?
Well, you get remnants in the George area, the what is called the Caimans group in that area, and of course the Kango group in the Oudtshoorn area is part of the Sildania belt generally. But then that's it. Then it all runs out to sea, and it would end up in some part of the Falkland Plateau. The Falkland Islands actually are part of the offshore Eastern Cape, KwaZulu-Natal. That's a fragment of that part of the continental crust. So that as soon as you get beyond, say, East London, you're onto the older Namakwa province crust coming out along the coast. Yeah.
Yeah, and then you pick up the Pan-African sort of 500 to 600 back in Mozambique, further up the coast.
In Mozambique, exactly. Yeah.
So can you see outcrops of Malmesbury group all the way to East London? Is that what you're saying?
No, you then get the Cape beyond sort of the George and Eisner area. You're into the Cape Fold Belt essentially along the coast, and then beyond that you get these older fragments of the Namakwa basement coming out in southern KwaZulu-Natal, Port Shepstone area.
Yeah, which is 1,200 million years old.
Yeah.
Yeah. Okay, Gert, are you happy?
I think so. John and Dave, thank you very much. As Letitia indicated, what a fascinating world, and what a privilege to have all you experts coming to enlighten us. Thank you. This is wonderful. Thank you for the preparation, and thank you for all of you who have joined us. I hope you found it equally interesting.
Yeah.
Well, unless there's a final question, I'm going to close the meeting now.
Okay, can I just thank all the guys that contributed, Gert, and thank you and the U3A for your support. This grouping works really well. And we really look forward to getting John Rogers, John Compton, Chris Hartnady out here in the future and getting them to take us to the next step. But thanks, everyone. We look forward to next week and seeing some of you again.
Thank you very much.
Thank you. Thank you, Dave.
Thank you, Dave.
John.
Thank you,
John. Sorry, John, just quickly, what was the idea for next week's field trip?
We're going to do the cliff path, start at Gearing's Point, but I'll send you the program, Gert, and you can, I'll discuss it with you and then we'll put it together. But that's the plan. So John will talk about the TMG and particularly the cliff path, and then we'll actually go and walk the cliff path. Is that correct, John?
Oh, that's
John,
correct. That's the plan. Depends how much time you want to spend on it. Can anything between half an hour and 2 or 3 hours. Depending on the size of the group. About 10 to 15 people is about ideal, I think, but we'll see what happens.
Very good. Thank you very much. And once again, goodbye to everybody. I'm going to end the meeting now.
Thanks, Letitia.
Thank you. Bye.
Bye.
Thanks, Chris.